Ignition sequence start.
Stanley, when is NASA gonna call about our big mission?
Any day now. I'm sure we'll get the call.
The weather is wonderful, and tonight the sky is going to be extra clear, which is great for all you stargazers.
Hey, I've got a great idea. Why don't we check out the stars ourselves? Maybe we'll discover something new up there and NASA will be super impressed.
Yeah, I want to know what a star is. What makes them shine?
Why is one star brighter than the other?
My mom used to tell me I was her bright shining star.
Oh, please.
Oh, and how old are stars? How long will they last?
Why wait? Let's take our new telescope and find out. I wonder how this thing works.
We all know that there are billions of stars in space. But even with a telescope, it's hard to get a good look at these twinkling lights in the sky. If you want to know what's going on up there, think of a sparkler. A chemical reaction makes it burn. It lasts for a while, and then burns out. That's the idea behind stars. Except sparklers last for about 30 seconds. Stars can last for billions of years.
So you see, Malcolm, stargazing is an exact and precise science. To use this telescope, you have to be a highly trained professional.
Oh, sure, Stanley. Most stars, like our sun for example, are primarily made up of two gases, hydrogen and helium. In the center, or core, of these stars, hydrogen reaches temperatures up to 15 million degrees Celsius. Let's see. According to my calculations, that's, hot!
That's 27 million degrees Fahrenheit, which is so hot that nuclear fusion takes place constantly. Nuclear fusion takes place at very high temperatures, when two or more nuclei of one element combine to form a different, heavier element. In the case of stars like our sun, we're talking about the fusion of hydrogen into helium.
I'm ready.
Okay, follow me now. In the core of the nearest star to Earth, our sun, 600 billion kilograms of hydrogen is converted every second into 595.8 billion kilograms of helium. That leaves 4.2 billion kilograms of hydrogen unaccounted for. Any ideas where it goes? Time's up! This is the part that is released as light and heat energy in all directions, and that's how a star shines.
Malcolm, it's important to know that stars come in different sizes. Our own sun, which of course is a star, is over 100 times larger in diameter than Earth. And it's only a medium-sized star. But some are up to 1,000 times larger than our sun. These stars are called supergiants. If our sun were a supergiant, it would extend all the way out to planet Mars.
Whoa! It's hard to imagine that some of those tiny specks of light are so enormous.
True, but some are much tinier than our sun, while some are even smaller than Earth. The smallest star is called a neutron star. Neutron stars have burned all their nuclear fuel and have collapsed. They can be as small as 12 kilometers in diameter. And Malcolm, we can tell a lot about a star just by observing its color.
We can?
Sure, a star's color is an indication of its temperature, just like the different colors of flames in a fireplace. For example, yellow stars like our sun have a surface temperature of about 6,000 degrees Celsius.
That's over 10,000 degrees Fahrenheit.
Yeah, but white stars are even hotter. And blue stars are the hottest. They can be anywhere from 20,000 to 50,000 degrees Celsius. On the other hand, red stars are the coolest stars. They average about 3,000 degrees Celsius.
That's still pretty hot.
Temperature is also an indication of a star's actual brightness, which is called its absolute magnitude. In most cases, the hotter the star, the higher its absolute magnitude. The cooler the star, the lower its absolute magnitude.
I hear that Sirius is the brightest star we can see from Earth.
It is bright, 23 times brighter than our sun, in fact. But of course, the brightest star we can see from Earth is our sun because it's so much closer. Even though Sirius has a much higher absolute magnitude, our sun has much higher apparent magnitude. Apparent magnitude is how scientists measure how stars appear to us. And get this, Sirius is not just one star, but two.
Ooh.
Sirius is part of a binary star system, two stars that circle around each other. Binary stars are very common in space.
They're like star buddies.
Yeah, but these buddies can get pretty explosive. Scientists think that when the gases from one of the stars in a binary system strike the surface of the companion star, it causes a nuclear explosion. Then tremendous amounts of heat, light, and gases burst into space, and the star gets so bright for a few days that on Earth it can appear in the sky like a brand new star. When this happens, it's called a nova, which means new. But of course, a nova is not really a new star at all. It's just the result of two old stars bumping into each other. According to my calculations, Sirius ought to be right over here.
Wow! I see a really bright star! Even brighter than Sirius! And it's red! This could be a new one! Is it on the map?
I doubt it, but that's probably because it's a radio tower.
Except for our sun, stars are too far away to be reached by space probes. So scientists use special instruments called spectroscopes to analyze starlight. You can make your own. You'll need a cardboard tube, two small squares of paper, one with a slit about 2 millimeters wide already cut into it, a pencil, some tape, 2 or 3 light sources, like a regular light bulb, a fluorescent bulb, and a candle, and the key ingredient is a 5-centimeter square diffraction grating. By the way, we all know the sun can damage our eyes if we look right at it. Do not ever use this instrument to look at the sun either. First, take the plain paper and punch a hole through the center of it with the pencil. Now tape this piece of paper to one end of the cardboard tube. Next, tape the second piece of paper with the narrow slit in it to the other end of the tube. Now tape the diffraction grating over the end of the tube which has the pencil hole punched in it. This will be your spectroscope. With it, you can see the different colors of your light sources. Move the tube around slowly until an image appears. When the different light sources pass through the diffraction grating, which is made up of tiny prisms, they are separated into different bands of color. This is just like a rainbow, which is the result of sunlight diffusing through moisture in the atmosphere. Your teacher may have other larger or higher quality spectroscopes than the one you built yourself. With these, you'll get an even better look at the different color bands in each light source. All light sources, including stars, give off different patterns of colored light, and each color represents a different chemical element. Using large telescopes and high-quality spectroscopes, scientists are able to analyze stars throughout the universe. They can learn about each star's chemical composition and temperature, and many other unique characteristics.
Malcolm, I think we should go over how a star is born.
If a star is born, it must have a mom and dad, right?
Very funny. I'm talking about the life cycle of stars, how most stars form and then burn out after many millions or billions of years.
Sure, I know.
Everything in the universe has a gravitational pull. even the particles in a large cloud of dust and gas called a nebula. As these particles attract each other, the nebula starts to rotate faster and faster until its density increases and its temperature rises. Eventually, nuclear fusion occurs.
The process of converting hydrogen into helium.
Right. Now the nebula begins to glow brightly. At this stage, it contracts a little and becomes stable. It is now called a main sequence star and will remain in this stage, probably shining for billions of years to come. Our sun is a main sequence star. As long as it has plenty of hydrogen fuel, fusion will continue and it will keep shining. However, when our sun's hydrogen supply runs low, the core will become unstable and contract. At the same time, the outer shell of the sun will start to expand as it cools down and begins to glow red. The star has now reached the red giant phase. So you see, Malcolm, all stars evolve exactly the same up until the red giant phase. Then it's the size of the star that determines what happens next.
Wait, I know. The red giant battles against the forces of evil. No, wait. The red giant conquers the galaxy with the help of Malcolm.
One more crack out of you and I'm cutting off your air hose.
I'll be good.
Now where was I? Okay, so after the star becomes a red giant, it takes one of two different paths depending on the size of the star. Medium-sized stars like our sun will eventually burn all of their hydrogen fuel and will collapse into a very dense white dwarf star. Nuclear fusion has stopped, but a lot of heat energy remains, so it still shines with a white-hot light. A typical white dwarf is smaller than Earth. Once all of the energy is gone, a white dwarf star cools down and ends its life as a cold, dark, dead star.
Okay, that's one ending. You said there were two.
Well, massive stars, much bigger than our sun, have a much more dramatic ending. They explode. These exploding stars are called supernovas and are brighter than 1 billion suns.
Whoa! Is this related to a nova star?
Nope, the two are very different. A supernova explosion happens because the core of the star collapses in less than a second, and the outer layers of the star are blown off in the explosion. What happens next depends on how big the star is to begin with. If the star is only a few times bigger than our sun, the core would collapse into a tiny, dense neutron star. But if the exploding star is much bigger than the sun, like supergiants, the massive gravitational pull will cause the star to collapse in on itself until it's a tiny point with zero volume but infinite density.
You mean?
Yes, a black hole. Truly one of the most mysterious objects in space. In fact, scientists can only observe black holes from the effects they have on other objects. As far as we can tell, the gravity of a black hole is so powerful that nothing can escape its pull, not even light. The tremendous force pulls gases from nearby stars into the holes. Some scientists also believe that black holes emit bursts of X-rays as matter is sucked in. Once something falls into a black hole, it can't get out, and it disappears from our universe forever.
Whoa! All that from one supernova!
And there's more. What I didn't tell you was that the outer layer that's blown off in the supernova explosion spreads out through space. It creates a new nebula that can cause the formation of new stars. And then the cycle can begin all over again.
So, I'm thinking we should come up with a name for our star.
Exactly. If it's an exploding star, we can call it Stanley's supernova.
Nah, we need something snazzier like Malcolm's supernova.
Oh yeah, real snazzy.
Thanks.
As far as we know, Malcolm, nothing in the universe is faster than the speed of light. It travels at about 300,000 kilometers a second. And as fast as that is, light from the sun still takes about 8 minutes to reach us.
So, if that's the case, how many minutes do you think it takes for light from another star to reach Earth?
Malcolm, we're not talking minutes, we're talking years. Light years. A light year is the distance light travels in 1 year, 9.5 trillion kilometers. Take Sirius, for example. It's 8.7 light years away, so light from that star takes over 8 years to reach Earth.
Let's say the Earth is here, and the Sun is here. The next closest star is 4.2 light years away. So where would it be? The nearest star to us, other than our Sun, is Proxima Centauri. It would be all the way out here, 6.7 kilometers or 4 miles away.
I'm ready.
Hey, did you know that some stars in space are over 100 million light years away? That means you're seeing light that began its journey to Earth when dinosaurs still roamed our planet. That's kind of like looking back in time.
Well, that was a bust, don't you think? Out all night stargazing and we didn't discover one new star.
Well, maybe next time we can try and discover an entire galaxy with billions and billions of stars.
Malcolm, where's the telescope?
You mean the big thing with the lens and the... Ugh. I'll be right back.
Hi, my name is Susan Stewart. I'm an astronomer. I work at the U.S. Naval Observatory in Washington, D.C. Basically, an observatory is a telescope under a dome. We have several instruments that go along with the telescope, like a computer to collect the data and different devices to collect the light from the end of the telescope. Astronomers use telescopes to study the light from distant objects. Basically, the telescopes enable us to collect the light and focus it on a device which will store the image so we can take the image to our computers and analyze it. Telescopes come in various sizes. They're almost like if you can envision a funnel. The bigger funnel you have, the more light you gather. Here at the Naval Observatory, we have a 12-inch telescope, a 24-inch telescope, and a 26-inch telescope. We study stars because our favorite star, the Sun, can affect our lives in many ways because it is our neighbor. And to understand the Sun is to understand all these millions of objects that are all around us.
Malcolm, do you realize that our Sun, the center of our solar system, is just one little star out of billions of stars in our home, the Milky Way galaxy? And the Milky Way is just one of about 50 billion other galaxies in the universe.
Whoa, I'm feeling pretty small right about now.
That's one reason why throughout history, astronomers have relied on constellations to help find their way around the night sky. Constellations are groups of stars that form a pattern. Many constellations were named thousands of years ago by ancient civilizations, based on mythical stories and people that were important to them.
Like Orion, a boastful hunter who was banished to the sky by angry gods. Or Ursa Major, a beautiful girl turned into a bear by a jealous goddess.
Over time, people noticed that these and other constellations appeared and disappeared throughout the year. So they used them as a way to predict seasonal changes. This is how the first calendars were made. Today's astronomers use constellations as a way to dissect the night sky into sections, making it easier to locate certain stars. Let's say astronomers want to find Sirius, the brightest star in the sky. They can find it based on their knowledge that it's located within the Canis Major, or the Big Dog constellation.
That is why Sirius is also known as the Dog Star.
Right. When you're dealing with billions of stars, constellations can be a big help. And to help find constellations and stars at different times of the year, you can use a sky calendar or star wheel.
Thank you, Mr. President. I will accept this award for discovering my own star.
The phone! The phone! Hello? Yes, this is Stanley. Malcolm is right here. Hey. Yes? Yes? Of course we can. Goodbye.
Who was that?
We have an assignment, and you're not going to believe this. It involves mapping the stars.
Wonderful. What time do we have to be there?
Not for a couple of hours.
We astronauts in training need our sleep.
Malcolm? Come on, Malcolm. Malcolm, we need to review everything we've learned. Now, what is a star and how does it shine?
Let's see. There are billions upon billions of stars out in space. Each star is a ball of very hot gases. Our sun is a star, but some other stars can be 1,000 times bigger than the sun, while others can be only a few kilometers wide. Stars shine as a result of nuclear fusion. In a star like our sun, this converts hydrogen into helium. In the process, energy is released in all directions as light and heat.
Very good. Now, why are some stars brighter than others?
There are a few possible reasons. The actual brightness of a star is related to its temperature. You can tell a star's temperature based on its color. Blue stars are usually the hottest, and red stars are usually the coolest. Another reason why a star is bright could be because it's very large, perhaps even a supergiant star. Or maybe it's really a binary star, two stars circling each other. And if a star shines very brightly for just a couple of days, it's probably a nova, a nuclear explosion between two stars bumping into each other.
Excellent. What about how old are stars and how long will they last?
Well, a star has a life cycle, a beginning, middle, and end, which can take billions of years to complete. Each star is formed from a nebula, a huge cloud of dust and gas. Then, most of them stabilize into main sequence stars and can shine for billions of years. The end of a star's life depends on its size. Main sequence stars will change into red giants when their outer shell expands, cools down, and glows red. Then, after all their hydrogen is burned up, they become white dwarfs. White dwarfs eventually lose all their heat energy and become dead stars. Really massive stars, on the other hand, will explode as supernovas. Then, depending on their original mass, either turn into neutron stars, which are very small and dense, or into black holes, which have zero volume and infinite density. Black holes allow nothing to escape, even light, and are some of the most mysterious objects in space.
Rock on, Malcolm. There's no doubt that we are definitely ready to map out the stars.
Star maps! Get your star maps here! Come and get them!
I can't believe this is our assignment. I'm an expert on stars in space, not movie stars.
Oh, it's not so bad. At least we get to know where all the movie stars live, right? Star maps! Get your maps to the stars' homes!
Oh, Malcolm.
I wonder where all the famous stars live around here. Ooh, there's one. Hello? Hello? Are you a star? Do we know where you live?
That's not a star, Malcolm.
Oh, that one is.
Oh, yeah, you're right.
Ooh, hello? Where's somebody exciting and beautiful? I want to see the stars up close. Star maps!
This may not be so bad.
This is great!
So you say. Gotcha.
What? Hey, take that!
Oh, you're going down.
Get this on the helmet.
Oh, take off the